Well, good afternoon, everybody. My name is Michael Norman. I am the director of the San Diego Supercomputer Center, and I'd like to talk to you today about Gordon, which is an upcoming architecture for data-intensive science. I am the principal investigator of this project, and Allan Snavely, who is the co-principal investigator, will also present in a tag team fashion. So let me begin by talking about what is Gordon. It's a new kind of supercomputer designed for data-intensive applications, and it's based on SSD flash memory as well as virtual shared memory software. And in a nutshell, it emphasizes memory and I/O capabilities over flops. It's designed to accelerate access to very large databases generated in all fields of science today, where very large would mean many terabytes of data. It is the NSF's most recent Track 2 award, and it is coming in summer 2011. So this machine does not exist yet. It has not been built, but we do have a small prototype of it that we're experimenting with right now. This slide here basically gives you the concept behind Gordon, and it's simply a depiction of the memory hierarchy in a modern microprocessor-based supercomputer, where at the top we have registers, which are very small but very fast in terms of memory access clocks, going down through the cache, the main memory, which takes about 100 cycles to access, and then there is a very large latency gap to go to disk, which is, of course, the largest storage we have, but it takes roughly 10,000 clock cycles to bring a word of memory from disk. And so looking at this, it's obvious that you'd like to fill this latency gap with some new technology, and that technology is flash SSD. Why Gordon? Why now? Well, of course, the flash SSD is becoming fast enough and cheap enough to deploy in large volumes, but what is really happening on the scientific frontier is we are being drowned in data. We talk about the data tsunami. It's the growth of digital data, which is exponential, and that exponential is driven by electronic technologies, driven by advances in digital detectors, ability to collect the data, ability to transmit the data, ability to store the data. We now have many terabytes of data from a variety of sources that we're struggling to analyze. Making sense of all of this data is the new imperative in science, computer-based science. And so that involves doing very large data analysis workflows, data mining, visual analytics, multiple database queries, multiple simultaneous queries, as well as on-demand data-driven applications. This table here compares and contrasts a high-performance computing system, which you would be familiar with Gordon, which we're calling a high-performance data system. So this is HPC versus HPD, if you will. So here we've got a number of attributes that we can talk about. Key metric for an HPC system is flops, top 500 and all that. For high-performance data, it's I/O ops, I/O operations per second. Architectural features of HPC systems are many small memory multi-core nodes, whereas for high-performance data, we would like fewer large memory SMP nodes. Why large memory? Because many of the applications do not parallelize well. Typical application on HPC is a numerical simulation. On HPD, it's a database query or data mining application. Concurrency, high levels of concurrency on HPC platforms, low or no concurrency on data-intensive applications. Data structures. Data is easily partitioned on a HPC system. For example, a grid is easily partitioned, whereas the data structures are typically not easily partitioned in data-intensive science. And just think about a very large graph as a data structure. Typical disk I/O patterns. On HPC, we have large block sequential reads and writes. to disk, which can be very efficient through striping, whereas high-performance data, if we have a very large database in memory, it's quite often small random reads, small block random access. Usage mode for the system, batch process for HPC. We imagine that HPD applications will be interactive. So at this point, I'm going to hand off to Allan Snavely to walk you through a few of the architectural elements of Gordon.
Is show you a little bit about our data challenge entry, which is based upon a prototype of Flash Gordon. As Mike just described, Flash Gordon won't be here until 2011. In the meantime, we want to see how well this Flash idea works today, and also work out some of the kinks or any issues that might arise between now and 2011, so that we wind up deploying the best possible system. And what we've done is we've built a small prototype of Flash Gordon, and this small prototype is based on 68 Nehalem processors that are dual data rate IB connected. And so in that way, it looks very generic. It looks like something that is common in academic centers and data centers. But Dash has a little bit of special sauce, I would call it, that makes it quite different from other systems, and I'll give you an idea of that. So the purpose, of course, is just to risk mitigate and prototype Flash Gordon, deal with some architectural issues. But the notion is to get data up off the spinning disk and closer to the processors. And Dash is a not insignificant system. It has 3 terabytes of DRAM and 4 terabytes of flash, so there's some real science that can be done as you'll see. Well, you may have seen graphs like this before. This shows what has been called redshift. Now, redshift in the universe means that our universe is flying apart. The stars are receding from us as our universe expands. A similar thing is going on in high-performance computing, whereby by Moore's law, processors get twice as fast every 18 months, but memory does not get twice as fast every 18 months, and that's shown on these curves here. Here you see over time the number of cycles that a floating point operation takes, and that's a decreasing exponential curve. And then you see the number of cycles of processor time that a memory access takes, and that hardly decreases with time. So, Moore's law is often described as a good thing, this wonderful increase in performance that we all get. But what if I told you that every 18 months processors are just twiddling their thumbs twice as fast waiting for data? Well, that is particularly true if the data is sitting up here. This line shows disk access time. This is worse than DRAM. This is bad enough. There's DRAM access time. Here's really bad, disk access time. That hardly ever gets any faster. In fact, disks do follow Moore's law in their own sort of peculiar way. They get twice as capacious. Their capacity goes up and doubles every 18 months, but their speed stays the same. Well, that leads us to a very peculiar situation. Look, every 18 months, by this pink line, the disk that you can get for the same dollar doubles in capacity. However, all the time by these green lines, the time to do a random access on that disk stays about the same. Once in a while it goes up a little bit. Back in like 2002 we started spinning platters faster, but it's just a little blip, hardly moved. And then here's an interesting metric. Take the size of the disk and ask how long would it take to visit every location on that disk in a random way, not a sequential way, but bounce around on that disk and touch every access, every address on that disk. Well, it takes longer and longer and longer to do that by Moore's law. And so it depends on your application. If your application is a true data mining application where the access pattern is not known in advance, you're actually falling behind all the time by Moore's law. And that's what Dash is trying to address and correct for certain kinds of science. So, we hear this phrase, drowning in a sea of data, and now we see why. It's due to a technical cause. It's due to the fact that you can fill up these disks with genomics data or astronomy data or what have you, but it actually takes longer and longer to access the data on the disk unless your access pattern is sequential. same slide as Mike showed. The basic idea of Dash as well as Flash Gordon is move some flash into the memory hierarchy. So remember I told you it's 64 Nehalem processors plus 4 more that are I.O. nodes. Each of these I.O. nodes has 2 controllers that each serve up 8 Intel X25 SSDs, so they're 64 gigabytes each. 16 times 64 is a terabyte, so there's a terabyte of flash sitting here. And then every 16 processors of Dash is put under this software called VSMP, which is from ScaleMP, a company whose booth is right next door. And that gives you shared memory and software across all of the memory of these 16 processors. So any core on any one of these processors can get to up to, well, it's 3/4 of a terabyte in total of shared memory. So now you have 2 levels of memory hierarchy beyond DRAM. You have a bigger sea of DRAM that is on shared processors across the IB interconnect, and then you have an additional terabyte of flash. What's the net result of that? Well, at a very low level, okay, so it's fun to say, if you have a data-intensive computer, how should it be ranked? Like, could there be a top 500 list for data-intensive computers? Well, we think there ought to be, and if there were, what would be the metric? It wouldn't be flops. We think it should be random I.O. ops. How many random I.O. operations per second can the system do? By that metric, Dash is very impressive. It's a fairly small system, but it can do up to 4 million I.O. ops, random I.O. ops, as measured by IOR, on up to 3/4 of a terabyte of DRAM. And then if 3/4 of a terabyte is not enough for you, and you still need more, then you fall out to an additional terabyte of flash, and that is a slower, but still, almost 100,000 random I/O ops per second. Much faster than disk. And this is the entry in the data challenge from SDSC based on these numbers. But I'll just leave you with one more thought before turning it back to Mike. What does this do for science? Well, let me show you a very interesting science problem that this is accelerating rapidly. There's several, but in the interest of time, I'll just show you one. We're working with a group at Berkeley that is looking for asteroids. It's looking for these objects that are flying around in space. And so, we whimsically say we're trying to predict when supercomputing will come to an end because an asteroid strikes the Earth and we're all extinct. How do they do this is very interesting. They are watching the sky all the time with a camera and taking pictures of the sky and taking pictures of known stars in the sky, and every once in a while one of these stars goes dim. It's called a transient. What has happened? An asteroid or a rock has passed in front of that star and made it go dim. They build up a huge database of these transients, and then they do data mining to try to connect the dots. You want to observe a number of these transients, connect the dots together, and say, oh, that must be due to a new asteroid that hasn't been discovered yet. Bottom line is, Dash has accelerated the kinds of queries that they do between 25 and 100-fold, depending on the nature of the query, because basically their huge database is sitting down on disk, and now it's sitting up on flash. So we're hoping to discover new asteroids in this way. Already we've sped up the search for them. And there's a lot more I could tell you about Dash, but let me turn it back to Mike now to talk about some future science that will be accelerated by Flash Gordon.